If you've ever felt that your body's energy system is this ultimate black box.
Yeah, some complex engine.
Exactly. An engine that determines whether you're ready to sprint
Yeah.
or just, ready for a nap. And that's really what metabolism is. It's like the entire financial system of your body.
It really is how you earn, save, and spend that energy.
And you shared a collection of fascinating sources with us on this. So our mission today is to take those insights and unlock the fundamental rules of that system. We're going straight to the core of how your body manages fuel.
It's the ultimate logistics operation. And when we talk about metabolism, we really have to look past the simple idea of just burning calories.
Right.
We're talking about every single chemical process that your cells need to survive. And it all boils down to this two-part process, a kind of the dynamic duo called catabolism and anabolism.
Okay, let's unpack this catabolism. It sounds destructive.
It is, in a way. It's the breaking down phase. So catabolism involves taking what you eat, your proteins, fats, carbohydrates.
All the raw materials.
All of them, and breaking them down with one explicit goal, to harvest energy. And we're not even at the final currency yet.
Right. We need to talk about the energy forms. The sources mention NADH and FADH2, which sound very technical.
They do, but you can think of them pretty simply. When you break down food, you release these high-energy electrons. NADH and FADH2 are just the carriers for those electrons.
So they're like energy vouchers.
That's a great way to put it. They're high-value vouchers that then get cashed in to produce ATP.
And ATP, that's the real money, the immediately spendable cash every cell can use.
Exactly. And that ATP is what drives the second phase, anabolism. Anabolism is constructive. It takes that ATP and uses it to synthesize everything your body needs.
Building new proteins, creating fat stores, assembling cell membranes.
Making new DNA, all of it. So the core insight here is that you can't really run both processes at full blast at the same time. The body is always deciding, are we building or are we breaking down?
So what controls that decision? Okay, let's unpack this starting with the master controls.
Right, so we have to shift from the mechanics to the regulators. And it's not one simple switch. It's regulated by three really critical inputs that are always interacting.
And the first one is the famous one, right? The hormones.
The hormonal system, yes, centered primarily in the pancreas. That's where you get insulin and glucagon. Your metabolism is critically dependent on whether you have high levels of insulin, which is the storage signal.
Or high glucagon, the mobilization signal.
Right. They're constantly measuring and adjusting.
Which makes perfect sense because the hormone levels must be driven by the second input, what's actually available, the substrates.
Precisely. Input number 2 is all about inventory. Is the blood full of glucose from that bagel you just ate? Are there amino acids flooding in from a protein shake?
Or what about fats? The sources mention triacylglycerols, or tags, being carried by chylomicrons.
Yes, and let's pause on that for a second.
Okay, what are chylomicrons?
They're essentially microscopic fat delivery trucks. When you eat fat, your gut packages it into these little lipoprotein bundles, and they enter the bloodstream to distribute that energy.
God.
So the body's constantly monitoring all these substrates. High levels activate storage pathways. Low levels activate mobilization.
Now, if that were the whole story, it'd be simple. Eat, store, fast, mobilize. But there's a crucial third input, one that can kind of override the whole system.
Yes, this is where it gets really interesting.
It was where stress comes in.
This third input comes straight from the brain, from the nervous system, specifically the hypothalamus. It's constantly sensing your environment, your stress level, and if it detects danger, trauma, even just chronic stress.
Or just the need to be highly alert.
It directs the release of stress hormones, primarily cortisol, norepinephrine, and epinephrine.
So this is the body's ultimate emergency override.
It really is. And it's crucial because it demands immediate energy, often prioritizing glucose mobilization, even if the other two inputs say we should be resting. It's all about setting the stage for rapid muscle action.
So we have the regulators, hormonal signals, the inventory in the blood, and the nervous system's stress override. Let's see how these define our two primary states, starting with metabolic state A, the well-fed state.
The definition here is simple. It's just elevated glucose in the bloodstream right after a meal.
And that glucose signal goes straight to the pancreas, which replies with the powerful storage signal, insulin.
Yes, insulin is the ultimate anabolic hormone. Job 1 is to clear that glucose from the blood so it immediately increases the uptake, especially by muscle and fat tissue.
And it's the master switch for storage in the liver, right? Walk us through that.
In the liver and muscle, insulin sends a twofold command. First, it activates glycogen synthesis.
That's taking the glucose units and chaining them together.
Right. into stored carbohydrate, or glycogen. Second, and this is key, it inhibits the breakdown of existing stores, a process called glycogenolysis. If new sugar is coming in, there's no reason to dismantle the inventory.
So you're maximizing storage and you're putting the brakes on breakdown all at once. What about fat tissue?
A very similar effect. Insulin ramps up triacylglycerol synthesis, so you're making and storing fat. And crucially, it locks down that stored fat by blocking a key enzyme. It's called hormone-sensitive lipase.
You don't need to remember the name.
No, but remember what it does. It's the master switch for dissolving fat stores. When insulin is high, that switch is locked firmly in the off position.
Okay, that system is incredibly efficient. All energy is moving inward. But the brain is always the exception. In this well-fed state, what's it doing?
The brain is the ultimate energy hog. It doesn't need insulin to get glucose. It just takes what it wants from the abundant supply in the blood. And when glucose is available, it uses it like premium fuel.
Oxidizing it all the way to CO2, producing a massive amount of energy.
A huge return. 38 ATPs per glucose molecule. It's operating at peak efficiency.
That's peak operation. But as soon as those glucose levels start dipping, the body has to flip the switch.
Yeah.
We transition now to metabolic state B, the fasting state.
And this state gets triggered whenever blood glucose falls. So after an overnight fast or just a long period without eating, the body just cannot tolerate low blood sugar.
Especially for the brain.
Exactly. So the storage signal, insulin, has to drop and the counter signals have to rise.
So low glucose triggers glucagon from the pancreas.
Correct. And at the same time, that nervous system input kicks in, so the adrenal glands start producing cortisol, epinephrine, and norepinephrine. All four of these are now working together to raise blood glucose.
So the body shifts from being a storage depot to an internal factory. What's this factory making?
Well, the liver becomes the primary glucose supplier for the whole body. Glucagon and epinephrine stimulate two major processes. First is glycogenolysis.
Breaking down those glycogen reserves we just stored, like eating your own stored carbs.
That's the rapid response. But once those reserves run low, say 12 to 24 hours in,
Then what?
then the liver activates its second critical process, gluconeogenesis. This is literally making new glucose
From scratch.
from scratch. From non-carbohydrate sources like lactate, glycerol, and even amino acids from broken down muscle protein. This is the body's long-term plan to keep blood sugar stable.
And while the liver is making new glucose, it's also making something else that's critical during a longer fast, ketone bodies.
Yes. Ketones are an alternative fuel source made from fatty acids. And the reason the body needs them is that while your muscles and liver can easily switch to running on fat, the brain can't.
And why is that? That seems like a really important limitation.
It comes down to the blood-brain barrier. Fatty acids are just too big to cross it easily to fuel the brain's neurons. So during a fast, the brain is limited. It can only use glucose and these ketone bodies.
So the rest of the body, the muscles, the heart, they switch to fatty acids to spare what little glucose is left for the brain.
Exactly. And the ketones provide that crucial backup fuel.
Let's circle back to that nervous system input here because it feels so relevant to modern life. If you're just stressed, stuck in traffic, on a deadline, your brain is interpreting that as a threat.
That's where cortisol and epinephrine become so important. They are ancient evolutionary hormones designed for fight or flight. If a lion is chasing you, your body doesn't care if you just ate.
It needs energy now.
It needs immediate explosive energy in your muscles. Cortisol specifically acts on the liver and muscle to start the breakdown process, glycogenolysis, even protein breakdown, to dump glucose into the bloodstream.
So chronic stress, whether it's a lion or a looming deadline, is basically forcing your body into a constant state of resource mobilization. It's hijacking the fasting signal.
It's hijacking it to raise blood sugar, which is a perfect insight into why managing stress is so intertwined with managing metabolism. The environment you live in, interpreted by your brain, has a direct hormonal override on whether you are storing energy or releasing it.
So if we connect all this to the bigger picture, we're really looking at a four-part symphony. Insulin, glucagon, epinephrine, and cortisol, all working to regulate blood glucose.
It's the essence of homeostasis. You have insulin, the storage chief, promoting uptake and building glycogen and fat after a meal, driving down high blood glucose.
And then you have the restoration crew. Glucagon, epinephrine, and cortisol, always ready to step in when the external supply stops.
Or when the brain just demands action. They get the liver to release its stored glycogen or manufacture new glucose, making sure that the most important organ, the brain, always has fuel.
So what does this all mean for you? It means your body is not just a passive energy recipient. It's an exquisitely sensitive regulator. It's making minute-to-minute decisions based not just on calories, but on subtle signals from the bloodstream and massive signals from your nervous system.
This really raises an important question to reflect on. If the evolutionary mechanism of cortisol and epinephrine is designed to dump sugar into your blood for a 30-second sprint from a predator, what's the long-term metabolic consequence when that stress response is on for weeks or months because of psychological pressure?
Right. The body can't tell the difference.
It can't.
It's truly incredible to think about the body's swift switch from using that massive energy output of 38 ATPs from external glucose right after a meal to generating new glucose and ketones just hours later. That change happens every single night when you sleep. Thank you for sharing these sources with us and letting us take this deep dive.